We have discussed in our previous lecture about configuration of the transistor. Now here we are going to discuss about DC load line and analysis. That's mean the DC load line analysis of the transistor. For this analysis we have selected that common emitter configuration of transistor because we know that transistor is an current controlled current source. That's when its output current is controlled with the help of input current. And in this case we have discussed that input current is IB, that is in microampere, so input resistance is high and output resistance is low. So the loss of the voltage at the input is less and loss of current, that's when current reduction in output is less. For the analysis I have selected NPN transistor and VCC is the voltage supplied to the collector terminal as in the diagram, and VBB is the voltage supplied to the base terminal. This is RL indicating load resistance, and in NPN transistor is arrow from base to emitter that represents direction of current. So that's why direction of current in the emitter is downward and in the base and at the base terminal is towards the base of the transistor and this is towards the collector terminal. Now VB is representing the voltage across base and emitter. VCC is representing voltage across collector and emitter. Now we need to write down equation for this circuit. So that's why first of all we will select this collector and emitter terminal as a loop and we will apply Kirchhoff voltage law. According to Kirchhoff voltage law, here VCC is the source and now current is moving from this positive terminal to the upside. So this will be positive and this will be negative. So it is minus ICRL, and again we will get the positive and negative terminal of VCE, then it is minus VCE is equal to 0. Then VCE plus ICRL is equal to VCC. From here we will get the value of VCE, that will be equal to VCC minus ICRL. See, we have selected the output terminal of common emitter configuration. So let's draw the graph for output characteristic of this transistor. This is our vertical axis and this is representing horizontal axis. Here we will select our in VCE and this is representing IC, that is milliampere. VCE in bold. Now the graph of this configuration output characteristic was in this manner. For the different value of base current. Now for different value of base current we have drawn the output characteristic of graph in this manner. Now we are going to compare our VCE according to this equation. When IC is equal to 0 milliampere, that means collector current is 0. In that case VCE is equal to VCC. I have marked that point. This is our VCC, and at maximum current That's mean this base emitter will be act as a short circuit. VCE is equal to 0. It's mean suppose we are taking that VCE, in that case IC will be equal to VCC upon RL. I have marked that point also. This point is representing VCC upon RL. Now we will match a straight line between these 2 points. This graph is representing the DC load line and its analysis. Now when VCE is 0, VCC minus ICRL will be 0 and IC will be equal to VCC upon RL. This gives the second point B on the, this is our point A and this is our point B on the vertical axis or collector current axis. And the slope of the graph, when we are going to study about slope of the graph, DC load line graph, is equal to the output changes from VCC upon RL to VCC. It's mean that VCC, that's mean यहाँ से क्या आ गया 0 minus VCC upon RL upon input changes from 0 to VCC, VCC minus 0, then result is equal to minus 1 upon RL. That's mean it's showing negative resistance. So let's do a quick revision. In DC load line analysis, we have write down the equation according to KVL. According to KVL, VCC minus ICRL minus VCE equal to 0. VCC plus ICRL is equal to VCC. Then VCE is equal to VCC minus ICRL. When VCE is 0, in that case IC equal to VCC upon RL. Slope of the graph is equal to 0 minus VCC upon RL upon VCC minus 0, that is equal to minus 1 upon RL. And when IC is 0 milliampere, then VCE equal to VCC. Now we will discuss biasing of transistor in our next lecture. Thank you.